Yeah. So we moved on from steel as a steel as a material to steel as a member. Therein, we studied what is a tension member, various types of tension members, what is a compression member, and various types of compression members. Uh, Now we are going to get to the third type of members, which are called as beams or girders. So beams are members that are subject to transverse loading, meaning that the loading is perpendicular to the longitudinal axis of the member, which causes bending stresses. Now, if you look at the small diagram or small sketch that is at the bottom right corner, it is nothing but the variation of bending stress along the depth of the section. Do you remember seeing this diagram before?
Yes.
Uh, okay. Uh, so the bending stress, unlike the axial stress, which is if it is a concentric axial stress, the stress is uniform throughout the section. But the bending stress is minimum at the neutral axis and it is maximum at the extreme fibers. Okay. So because of this, you see that beams are most efficient when the area is distributed to be as far as possible from the neutral axis, because this is the region that is going to be most stressed, and this is the region that is relatively lesser stressed in bending, and therefore we see most of the girders that we use are I sections, and that is because of the kind of stress variation or the bending stress variation along the depth of the section. Now, as a result of this type of loading, what happens is the measure of the material remains unstressed. You see this green portion, it does not have a lot of stress. And therefore, we could say that perhaps a beam is not the most efficient member. Now, if we talk about now, if the same section had been in tension, the stress variation would be something like this, wherein you would have a uniform stress all over the section, meaning that the entire section is participating in resisting tension. But in bending, it is only this it is only this portion that is largely stressed, and it is this portion which is relatively unstressed. And therefore, beam is not one of the most efficient members that we come across. Uh, and moreover, you see the bending moment. Now, if I draw the bending moment diagram of a simply supported beam, uh, say a uniformly distributed load, the bending moment diagram looks something like this. Anybody who can tell me what is the magnitude here at the center? Anybody? Yeah,
Zero.
what is it?
It's uh, blue L square by 4 or
So WL square by 8. So this is the value of bending moment at the center. Now you see this maximum value is only at one location, but our section is going to be the same throughout the length of the beam. Our section is not going to differ. And you see this is particularly in this portion, the beam is the beam is relatively unstressed. And therefore, we could say that uh, beams or girders are not really the most efficient types of members. Uh, so these are the typical cross sections that are used as beams. Um Mostly in normal buildings, we have rolled sections, and if it is if it is a heavy loaded structure, for example, bridges, then in that case we have these composite members, which are constructed of either it may be a built-up plate section, or it may be a combination of this type of an I section, channel section, and so on. The next type is what are called as beam columns. Now, if you recall, we saw last time that that columns which are particularly located along the edge of the building or at the corners of the building are subject to bending moment in addition to axial load because of what we call as unbalanced moment. So there is loading only on one side of that column, and therefore, by the virtue of this loading, it is subject to axial load plus bending moment. And such members which are subject to significant bending in addition to axial load are called as beam columns. Now, it may be designed as a beam or it may be designed as a column primarily and then check for the other aspect. So the type of the member to be used depends upon the predominating load. If bending dominates, then it is designed as a beam and checked as a column. And if the actual flow dominates, then the other way. And like we looked at in the last lecture, the bending may be uniaxial or biaxial. In very simple terms, if it is an edge column, so it will have bending only in one direction, and in that case, the column would be uniaxial. However, if the bending, if it's say a corner column, the bending would be in both directions, and the column would be biaxial. Now we move on from steel as a member to steel as a structure. So the basic types of structure could be classified as frame structures, uh, shell structures, and suspension structures. Now, many unusual structures utilizing various combinations of frame, shell, and suspension types have been built. However, a typical designer must principally understand the behavior and design of frame structure. And we are going to, basically, this course is devoted to the behavior and design of elements in what are called as frame structures. Now, in a frame structures, elements may consist of tension members, compression members or columns, beams and beam columns. Now, these are the most typical type of buildings fall under this category. And simple single-story buildings, multi-story buildings, industrial buildings, bridges are all more or less frame structures. Uh, Now, shell type of structures serves as a use. Uh, Now, these serves as form as well as function. A common type where main stresses are tensile is containment vessels, which are used to store liquids. Now, in these type of structures, axial forces predominate. Common examples of shell type of structures are water tanks, bin, gas cylinders, hulls of ships, and so on. Now, these type of structures are under what are called as hoop stresses. Have you heard of this term before? So when we have oh, this is a very poor diagram, I know, but this is the best I've got right now. So when we have a cylindrical structure, say a water tank, now water exerts pressure in all the directions. And because of this pressure, this vessel is under what is called as hoop stress, which is a tensile stress along the perimeter of the structure. So shell type of structures are mainly under hoop stress. Then suspension type. Now, in these type of structures, the name itself suggests that axial tension predominates. Uh, in the majority of these types of structures, tension cables are the main supporting elements. Examples of these include suspension bridges, cable supported tubes, etc. Even though the structure is called suspension type, but some part of the structure may be frame. For example, the picture that you see in the background, though it is a suspended roof, but it is suspended through a frame structure. Even when we talk about suspension bridges, say the Golden Gate Bridge, though the deck is suspended, but the suspension cable itself rests on a frame structure, which is the pier of the bridge. Now, when we say design, so structural design is a little different from architectural design. And design is basically a process of optimization. When we are talking about optimizing something, we have to we have to set some parameters as to if these parameters are satisfied, I'll say that my structure is optimized. Okay. So when it comes to structural design, uh, the design consideration includes first and the most important is whatever you build, it has to be at minimum possible cost. It has to weigh minimum because if it weighs minimum, it is going to require less material and it is going to need a lighter foundation and that is going to save a lot of money. Then it should be constructed in minimum time. It should require minimum efforts in terms of labor, and it should have maximum operational efficiency. These are the basic design considerations before starting a structural design. So there are a set of principles. For example, now last time someone asked me as to for how long do we design or what is the design life of a structure, and I answered it to be from 50 to 75 years. So when I say that the life of a structure is 50 to 75 years, what am I talking about? When do I say that the structure is no longer usable, or or under what conditions do I say that this yes the structure can be used safely? So when we're talking about the safety of the structure, we are particularly talking about the strength of the members in the structure as a whole. We are talking about stability and we are talking about structural integrity, meaning that the structure should act as say as a single what we can say a single unit and not just a set of different members. So this is when we say a structure is safe, when it is sufficiently strong, when it is sufficiently stable, and when it has sufficient structural integrity. Now, next we see that the structure is serviceable when it has adequate stiffness, meaning that it does not undergo a lot of deflection and it has what is called as durability. That is, it's not the case that a number of members of the structure need maintenance now and then. So it has to be durable. Uh, the next point is it has to be economically viable. And uh, unfortunately, the factor which comes first for you comes last for us is that it should be aesthetically pleasing and sustainable. Uh, so when we say a structure should be safe, what we principally mean is that the possibility of collapse should be acceptably low and not under the normal conditions of expected loads, but also under less frequent loads like earthquakes or extreme winds and accidental loads like blast and impact. Now, the photo that you see in the background, I'm not sure if you have seen this before, is from a building in China that collapsed even without any loading. So I mean, even without any live loading, or even without under an earthquake or a very strong wind or typhoon, so on. So what happened is they constructed this particular building and they started digging on one side. So because of that particular digging, what happened is the foundation was loaded on one side because there was soil on one side and there was no soil on the other side. And that led to lateral pressure. I hope you understand what is lateral pressure. So any pressure that is exerted from the side is called as lateral pressure. And because of this differential lateral pressure, the foundation could not take it and the building just collapsed as it is. Now you can see, though the members were strong, the structure as a system was strong, but it was not stable, or because of the kind of loading that it was subjected to, for which it was not designed. And therefore, it is quintessential that we consider safety in terms of strength, stability, and structural integrity. Um, yes. So the structure as a whole should be stable under all conditions, and it should have any questions. And it should have what is called as redundancy for the distribution of loads, meaning that if one part of the structure fails due to some reason, it should be uh, able to redistribute the loads to other parts of the structure, meaning that it should minimize what is called as progressive collapse. Uh, so this is a small video wherein the structure uh, was strong, the members were in place, but then there's something which was very unprecedented that caused the failure of this structure. Can you hear the audio?
Oh no.
No,
Hmm.
still less.
I think so. While sharing only, you will get the option to share audio also. So check it out.
Sorry.
Okay, now. Is the video lagging?
Yes.
A little bit.
Okay, okay, just a moment. So, any questions?
Yeah, hi Faisal. I had a question.
Yeah.
So, in the video, we saw that the bridge was not loaded with vehicles. What if there would have been the whole bridge would have been covered with vehicles?
Sorry. Can you please repeat? I do not understand your question.
I'm saying if there would have been vehicles on the bridge, then how
Yeah.
would have that affected the train?
So first of all, did you guys understand why the bridge failed?
Was it because of resonance?
Was it because of?
Resonance?
Yes. So designing a structure for a possible resonance because of wind was uh, was not really a norm then. It was the first time that it happened that we witnessed such a type of failure. Now, wind or earthquakes have their own frequencies, and buildings or say bridges have their own time period, have their own natural time period, or have their own frequency. Okay, so when I say it has its own time period, what it means in very raw terms is that a building that is short would have a very small time period as compared to a building which is very tall. Okay, meaning that if a tall building is subject to lateral forces, it will, say if it sways, it will take longer to get back to its original position as compared to a building that is short. I hope this is very simple to imagine. So a taller building has a greater time period or a lesser frequency. So basically every structure or every building has its own frequency. And what happened in this particular case is the frequency of the wind happened to match with the frequency or the time period of the bridge, because of which what happened is resonance. And because of this resonance, the structure or the deck started swaying uncontrollably, and after some time it gave up. And it was discovered that the more you try to resist wind, the more force it is going to exert. So a lot of bridges that have been designed after have what is called as, or what can we loosely say, a deck that has openings in between. Say a truss deck which does not provide a lot of resistance to wind. If you don't see, we have looked at this before. Whenever there is resistance, there is stress. If you allow wind to pass, it is not going to have resistance. If you do not let it pass, it is going to exert force. So a lot of bridges, a lot of long span bridges that have designed after this have taken care of this particular aspect, and they try to let the wind flow freely as much as possible. So going back to the original question as to what would happen if we would have traffic on it. Maybe if we would have traffic, in that case, the frequency of the bridge might have been a little different because now it is loaded. It has it, and it would kind of change the way it behaved when there was no traffic. So fortunately, there was. I mean, we just have to sort of uh, just be thankful that there was no traffic when this happened, because I believe it wouldn't make a lot of difference because uh, it wouldn't really change the frequency of the structure a lot if it would be loaded throughout its span. So I think the behavior wouldn't be much different if it would have been loaded.
Okay, thank you.
This reminds me of a question that Shreyans has asked me. Shreyans had asked me last time. Please excuse me if I take an incorrect name. About the World Trade Centers and why it collapsed, even though the core was concrete. So I haven't had a time to look into it, but I promise I'll get back to you in the next lecture, and I'll answer that question for you. Any more questions on the video we saw?
Hello.
Yeah.
Yeah,
Who is it?
about that World Trade Center. So we had a presentation last sem for it. So
Okay.
in that we saw videos. So in that it was basically explaining that the plane crash actually. So for each building it was different. So for one building it was a failure of the outer core and outer tube, and for one
Yeah.
building it was the inner tube.
Okay.
And so what the plane did was wiped out 3 to 5 floors in middle, and
Yeah.
because of the crash of the upper floors, it actually collapsed.
Okay. Okay.
So which was different from that building which had center concrete core and the outer steel core, which had just fire and no like crash in it. So that could be
Yeah. Yeah. So, who is it, by the way?
Shreyansh.
Okay. Okay. You found the answer. Okay. Great. So, I think he's right because I think he's right because what he's trying to say is because there was a physical damage uh, to the core, and it was not just a fire. So it was a physical damage plus fire, and that is something that caused collapse of the towers. Okay. You only asked the question, right? Or
Yeah.
yeah. Okay. 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 So thank you for answering it for me. Okay. So the next aspect is any more questions?
Hello.
Yeah.
Yeah, I had a question. Are no, two things different? Having natural frequency and the lightness of the like allowing of the wind to flow through the structure. Because this bridge seemed very light, like it wasn't bulky or resisting the force of wind. I think. So what was
So
exactly happening?
the portion of the bridge that resists wind is the deck. Okay. If it is a solid belt, then what is happening is the entire belt is resisting wind from flowing. And because the wind is stopped, it would flow, it would have to go above and below the deck. And it creates turbulence. And that is because of what? The deck started swinging. Okay.
Yes,
Had
yes.
the,
Okay.
had it been an open had it been an open structure wherein the deck would not act as a solid belt, but say a perforated one, then
Mm-hmm.
what would happen is a majority of wind would pass without exerting a lot of pressure on the deck.
Mm-hmm. Okay. Yes.
And that is the reason why the deck started swinging. Now this is different from a structure having its own time period. The time period is a function of how stiff the structure is. So that is a little different from this phenomenon of resisting wind. Did I answer your question?
Yes, yes. Yeah.
What's your name?
Sarthak.
Okay, Sarthak. Thanks. Any more
Uh,
questions?
yeah.
Yeah, I have
So
Yeah.
one.
why did the bridge took so many waves to break? Like, why didn't it break in the first or second? Because it was like truss deck, na? So the rivets could have easily torn off with
Uh,
that kind of movement.
Actually, I'm not sure what the system was, but I think it does not seem to be a truss deck. It is just a deck that is suspended. It seems to be a concrete deck that is suspended uh, from the main cables. So
So even
the reason,
concrete took that kind of deflection.
yes, the reason why it did not break in the first go is because it as a material has some inherent strength, right? And so it swayed before reaching its material strength or before uh, obviously it is not now no structure is going to fail at the first instance. It has some inherent strength which will keep it together, and then after a certain amount of cycles or after a certain magnitude of deflection it is going to give up. Did I answer your question?
Yeah.
What's your name?
Rahul.
Rahul. Okay. Yeah, somebody else had a question.
Yeah, is it possible for the steel inside a column or a beam to melt due to extreme fires when there are physical damage to the member and the concrete peels away?
Okay. So everything depends upon what is the duration of the fire. If the fire is say about 2 to 4 hours of fire, uh, concrete may sustain it, or concrete may be able to resist this fire. But if it's a very long fire, 7, 8 hours, 10 hours, 12 hours fire, then ultimately the steel, the reinforcement within concrete is going to give up, and then concrete as the column as a member is going to give up, and naturally the steel which is embedded in that concrete is going to be subjected to the fire, and ultimately it is going to give up. So it all depends on what is the duration of the fire. Did I
Okay,
answer
all
your
right.
question?
Yeah.
What's your name?
Mohit.
Mohit. Okay. Thanks, Mohit. Okay. Any more questions?
Yeah, we actually had a question about the World Trade Center that in spite of having a concrete core,
Yeah.
still the building like it failed. So like that was the question we had for the World Trade Center.
Yeah.
Yeah. So can you please address that question maybe?
I think Shreyansh just answered the question when he said that it was not just the fire, it was also the physical damage that the plane caused to the core.
Okay.
Had
Okay.
it been only fire, perhaps we would see that the uh, uh, being being subject to a lesser amount of damage, but it was fire plus the physical damage which caused the failure of the core.
Okay.
And the floor, the collapsing of the floors above, like
Yeah.
the
So
dead load.
yes, the flaws just piled upon one another, exerting a lot of dead load. Shreyans, would you add anything further? Okay.
So,
Yeah. Go on. Go on.
the concrete core, it seemed like the concrete core, even if it was such a dead load, it might not. Matlab, the concrete core is quite strong and it was quite dense. So uh, I didn't understood that how such a core of such a strong building collapsed because of weight. Uh, yeah, it was a little surprising.
Okay. Is this another question?
Yeah, matlab, I saw the video and I understood ki why it happened, but matlab, structurally why it happened I didn't. Matlab, how it happened I understood, but why did it happen I didn't understood.
Okay. So just give me some time to read about it, do some research, and I'll get back to you next section.
There was also an allegation that the fuel had leaked through the floors, like the kerosene of the plane. It had leaked through the floors, and and it spread around the core itself, so it melted any steel that was around the core, and even that was one of the causes.
Yeah. So principally, we are talking about fire here, and why the magnitude of the fire increased because of leakage of fuel and so on. Okay. Any more questions? Okay, great. Moving on. So this was about strength. The next aspect is serviceability, which is related to usability of a building. Now, we don't want a structure that is very strong, that is going to last 50 years, but something that we cannot comfortably use. For example, if there's a structure that has a lot of that is strong, it's not going to fall, but it has deflected a lot. Naturally, we cannot comfortably use it. If there's a structure that has a lot of uh, cracking, naturally we'll not be able to will not be comfortable using the structure, or any structure that kind of transmits vibration. No, we're not comfortable with this. So it is not just about strength, but it is also about serviceability, that we should be able to comfortably use this structure throughout the design life. So this is next aspect, which deals with deflection, cracking, vibration, fire protection, and so on. Now this is another one. I think it's better if I play it in the player. Did you understand the difference between this one and the last one? Can you hear me?
Yeah, now we can.
Yeah, okay. So any questions here?
We couldn't really see what happened. Like the video was lagging.
Okay, I'll just play it one more time. Just let me know if you don't. Hello, can you hear me?
Yeah,
Your voice, yeah.
Yeah. Could you see it now?
yeah.
Okay. So any questions on this one?
The bridge was deflecting again, wasn't it?
Yes. But this time it was deflecting because of the oscillations that were set, or the oscillations that were passed on to the bridge because of the motion of the pedestrians. Now, if you if you just want to experience this phenomenon, you could just stand along near the center of, say, any pedestrian bridge which is at a railway station. You just stand there for a while. Okay, not on the other bridge, any other. Okay, you just stand at the center, and you could actually feel the vibrations, or you could actually feel the bridge deflecting a little. Has any one of you experienced this before?
Yes.
Even if you stand, say, even if you happen to stand at the center of any of the flyovers, and say a very heavy truck passes by, you could actually experience the bridge kind of experiencing some kind of motion. What happened? What happened here?
Actually, even in the studio, when someone jumps from the table on the ground, we experience.
You can experience it in metro when metro passes.
Yes. So, so what happened here is the this type of loading was unchoreographed. Like so many people walking it over, and then even we have a frequency while walking, and when we design pedestrian bridges, we make sure that the frequency of walking does not match with the frequency of the bridge. Um, and so many people walking together at the same time kind of passed on oscillations, and the bridge started oscillating, and the what we can say, the magnitude of oscillations increased with time, and this very beautiful bridge had to be shut down, then it was repaired, and then it was open again to public. So it did not collapse per se, but it was not serviceable, or it could not be comfortably used, and therefore serviceability also plays an important part when we are designing a structure. The another aspect is economy. Now we could design a structure that will last for 300 years. We could design a structure that will deflect by less than 1 mm, but it comes at a cost, and we have to kind of do the mathematics as to is it really worth it, or is it really need to be that conservative, is it really need to be that safe. So economy plays an important part in 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 designing any structure. So increasing the design margins of safety can enhance safety and serviceability, but increases the cost of the structure. So these are the design principles. Any questions here? Nextly, we are going to look at, having known what I want to achieve, there has to be a standard way of achieving those objectives. Okay, and this standard ways are what are called as design philosophies. Now we are not going to get into the theory per se, but we are just going to understand the basics of what is called as a limit states method. Okay, conventionally, or the first standard method that has been used is what is called as working stress method. Over time, we moved to what is called as ultimate load method, and currently, what we have is called as limit states method. So we are not going to go into the theory of these, the mathematics of this, just the basics that will help us design, and that will help us understand why we are taking these particular factors in a number of equations that we are going to use. So just a basic glance at what is called as limit states method. Quick question: have you heard of this term before?
No.
Okay. Uh, so just to give you a heads up, when you get a paper from the university, there is always a note that you could either solve the numericals by working stress method or limit states method. So what we are going to follow in our course is the limit state method, which is actually used in practice. Yes, working stress method is also used, but in a very limited applications and in a very small extent. It is almost obsolete now, and like almost all the structures are designed as per limit states method. Okay, so since we just saw that a structure does not have to be only strong, but it also has to be serviceable. So there are a number of limit states of strength and limit states of serviceability. Now let us understand what is a limit state. Okay, I'm just going to read this. Uh, a limit state is a state of impending failure, meaning that it is a state when the structure is about to fail but has not failed. So a limit state is a state of impending failure. If we achieve the state, the structure ceases to perform its intended function satisfactorily, either in terms of safety or serviceability. That is, it either collapses or becomes unserviceable. So our objective is we have set a limit states of strengths and limit states of serviceability. Our objective is to make sure that the structure does not achieve any of these limit states. Okay, if it achieves any of this state, the structure can either be called as unsafe or it can be called as unserviceable. Uh, could I explain it? Could you understand this? Could you understand what a limit state is?
Yeah.
Yeah.
Simple, right? It is just some state that we do not want to achieve. For example, take an example of our cell phones. So a limit state of collapse could be breaking of your screen. Okay, that's a limit state of collapse, and that is going to need some serious structural repairs before it can be used. Then limit state of serviceability may be your phone hanging a lot, right? You can still use it, but it's not comfortable. You have to kind of reboot the system. You have to do a factory reset, or there's some repair that you have to do so that it is comfortable for you to use. So you can say hanging of a phone is a limit state of serviceability for the phone, and any physical damage that is caused to the phone is a limit state of safety of the phone. Similarly, there are limit states of safety for a structure and serviceability for a structure. So in steel construction, limit states of strength include loss of strength because of yielding. I hope you understand what is yielding. It just the material yields, the strain increases without an increase in the stress. Buckling or transfer into a mechanism, meaning that the structure cannot take any more load. The loss of stability against overturning and sway. Loss of stability, the example of the building in China that we saw, which lost its stability and overturned because of differential lateral pressure. Then failure by excessive deformation or rupture. Uh, then fracture due to fatigue. Fatigue we saw last time when we discussed the example of a train bridge, which undergoes a number of cycles of loading, which causes fatigue, and then brittle fracture. Okay, these are limit states of strength in steel. We will have a different set of limit states of strength for a concrete building. The limit states of serviceability include excessive deformation and deflection, vibration, which are induced, which include wind-induced oscillation. We could also say pedestrian-induced oscillation, flow vibration, etc. Then repairable damage due to fatigue, that is cracking, corrosion and subsequent loss of durability, fire. So these are the limit states of serviceability. If the building achieves one of these states, it can always be repaired and used. Okay. So now let us try to understand how how we how we make sure that the structure does not achieve these limit states. Okay. So we have a certain demand. When I say demand, the demand is in terms of loads. Okay. When we apply loads, the various members are going to experience internal stresses. It may be in terms of axial stresses, bending moments, shear forces, torsional stresses, and so on. Everything is clubbed in demand. Okay? And capacity is what is the inherent strength of the material and the member. Okay, this might be a little uh, new for you. So at any point of time, if you don't understand what I'm saying, just stop me. Okay, I'll maybe explain it in some other terms. Okay, so we have a capacity and we have demand. Theoretically, for a very optimum design, demand should be equal to capacity. Simple, but we have to have some margin of safety, right? The capacity should always be greater than demand, else we cannot be able to, the structure may not be able to sustain any unprecedented load. So there has to be certain margins of safety, and therefore the capacity should be greater than demand. But the question is, how much should the capacity be greater than demand? And the capacity is function of what the material you're using and the geometry of the material. That is, what are the dimensions of various members, how they are connected to each other, and so on. And the demand is in terms of loads and deformations. So one thing is established, simple, the capacity should always be greater than demand, right? But how much? Now, limit states method tries to answer this question. Now, though we say that it is M40 concrete or say it is M80 concrete, does it mean that when you test that particular block, it is going to give you a strength of M80 or M40? So in a majority of cases, that does not happen. There is an inherent uncertainty in the material strength. Okay, concrete, for example, is a very heterogeneous material. There you could have sand from one place, coarse aggregate from one place, cement from one place, water from one place. So it's a very heterogeneous material. When you put it together, you design it. It is very uh, what you could say. It is not probable that when a concrete is rated as M40, you test it, it is going to fail at 40. So there are uncertainties that are associated with the material. Now, steel comparatively is a more homogeneous material, and relatively it has a more uniform behavior as compared to concrete. But material inherently has a lot of uncertainties in terms of its behavior. So there is something called as characteristic strength. To understand the meaning of this, let us take a small example. If we have, say, 100 blocks of concrete, have you seen a concrete block before that is used for testing? Have you seen a concrete cube that is used for testing? Right? Okay, it is concrete blocks like these, which are put in the universal testing machine. And in steel, we pull the material. In concrete, we push the material because we want to test concrete. So a simple example to understand this concept, say we have 100 blocks of concrete, okay, which are casted from the same, we could say from the same fresh concrete, okay. When we say characteristic strength, it is that value of strength. Okay, so if we have 100 blocks, we test these blocks one by one. We apply compressive force, we crush these blocks, and we just note the load at which the failure occurs. Okay, now we have 100 values of loads. Characteristic strength is that value of strength or that value of load which which at least 95 of these blocks will have a failure load greater than this value. Okay, we have tested 100 blocks, we have 100 values of loads at which they are failing. So characteristic strength is that value of load above which 95 of those blocks uh, or, or, or that value of load, that 95 of these blocks have a value of load greater than this particular number. That is called as a characteristic strength. So only 5 blocks would fail at a lesser value of load. So when we say M40 concrete, what that means is if I test 100 blocks that are designed for M40 concrete, at least 95 of those would have a strength of more than 40, and only 5 of them would have a strength of less than 40. So that is what is called as characteristic strength. Okay. Uh, did you guys understand? Any questions?
Can you just repeat the characteristic, the last part again?
Okay. So when we say that a concrete is M40 concrete, it means that the characteristic strength of concrete is 40 megapascals. Loosely meaning that if we test 100 blocks of this particular strength, 95 of them would have a strength of greater than 40, and only it is probably only 5 of them would have a strength of less than 40. So this is what 40 means, and this is characteristic strength.
Oh, okay, all right. Thanks. Got it.
Mohit, did you understand?
Yeah, got it, got it. Thanks.
Any more questions? Uh, Sorry, I cannot hear you properly. Is someone talking? I cannot hear properly. Okay, are you guys awake?
Yeah, I think
Yeah.
somebody's mic was
Yeah.
unmuted by mistake.
Okay, okay. So this is what is characteristic strength. If you don't understand, ask questions. Maybe go through the presentation and later ask questions. No problem. Now, so this was about capacity. Okay, strength is capacity. Then we talk about loads, which is the demand. Like we have characteristic strength, we have what is called as characteristic load. So it is that value of load which has a 95% probability of not being exceeded during life of the structure. Meaning that if you're designing the college building for a certain live load, okay, say you design it for 4 kilonewton per meter square, means that, and say the design life of this building is 100 years. So there is a 95% probability that this load will never be exceeded during the life of the structure. Do you understand the difference? So what we are doing is we are taking such a value of load that has only 5% probability of being exceeded during the life of the structure. So what we are basically doing is we are sort of underestimating the strength and we are overestimating the load. Okay, so you can see The graph on the left is load effect. The graph on the right is resistance effect. Left is demand, right is capacity. The capacity should always be greater than demand. And the greater the difference between these, the greater is the safety margin. If the safety margin is a lot, means that the structure is uneconomical. Okay? So, what limit states say is we could have this overlap, and this point is the 5% uh, characteristic is the characteristic strength value for this blue graph and the characteristic load value for the load graph, and the shaded portion that you see is the possibility of failure. Any questions?
Hello.
Yeah.
I didn't actually understand the difference between characteristic load and characteristic capacity.
Okay. Anybody else who did not understand?
Maybe you could repeat once again.
Okay. So characteristic strength is capacity. Okay, is capacity of the material. So characteristic strength is that value below which not more than 5% of the test results are expected to fall. Meaning 90, if we test 100 samples, 95 samples would have a strength of more than this value. Okay, let me put it this way. Do you remember the graph of the quiz that we did last time?
The characteristic strength doesn't have a value, does it? It's
It
just
has
a
a value. It has a
okay.
value. So when we say M40 concrete, 40 is the characteristic strength. So let us look at it this way. Just a minute.
No, but it's a theoretical value. No, it's not used for any calculations, is it?
It is used for all calculations. Okay,
Oh,
just
okay.
let us just look at this graph. Okay. You see, this graph is more or less like a Gaussian curve. Okay. So whenever you do an experiment or whenever you collect data, you will see a graph like this, wherein very small number of people, say for this particular example, very small number of students have got a very low score, very small number of people have got a very high score, and then we have a large number of people having a score that is average. Similarly, if I look at this graph, if I test 100 blocks of concrete, I'm going to get a graph like this. Okay, and this particular graph is called as a Gaussian curve or a normal curve. Whenever we collect some data from an experiment and try to plot this is the kind of graph that you're going to get. So what I do is I sort of fix what should be the passing marking. Okay, I see that okay, 95% of you have got more than 2.5 points. Okay, so I will set this as the cutoff. So 2.5 is the passing marks. Okay, you could say 2.5 is the characteristic passing value. Similarly, when I test 100 blocks and I sort of get this type of a graph, I say that okay, 95% of these blocks have a value of more than this. So I set this as my characteristic strength, and this is that value which I designate to that particular concrete. I would say this is M40 concrete, meaning that test 100 blocks, at least 95 have to have a capacity of more than 40 megapascal. Do you get it?
Yeah.
And when we are talking about loads, okay, see, it's very simple. There's capacity, there's demand. One thing is established, the demand should always be greater than capacity. Okay, so we are going to look at the minimum strength the material will have and we are going to look at the maximum loads that are going to be exerted. Do you understand?
You said capacity has to be greater than demand, no?
Capacity has to be greater than demand. So we would look at what is the least capacity of the material, and we would look at what is the maximum load, and then we will make sure that the least capacity of the material is greater than the maximum load. Do you understand the difference? So this, the arrow that you see here is the least capacity of the material. The arrow that you see here is the maximum amount of load, and we have to make sure that this, the least capacity, is can cater to the maximum value of load. We always underestimate capacity, and therefore we have considered a point that is on the left end, or that is on the left arm of the normal curve. So we always underestimate capacity, and we always overestimate loads. So we design it in such a way that even the lower value of capacity can handle a higher value of demand. And when this happens, this is in this region, we say that the structure is safe. And only in this red region, which has a very less probability, wherein uh, the loading is greater than the 95% probability loading or the characteristic loading, uh, and it is only 5% chance that the structure will fail. Do you understand more, or now it's more confusing?
It is a little bit confusing.
It is a little bit confusing. Okay.
Like in theory, it is understandable, but like in graph form, it would difficult to.
Okay. Okay. So forget so forget about these graphs for a moment. Okay. Let us try to understand it this way. Okay. So I have used a certain grade of concrete for the college building. Okay. And what I do is I every day I kind of go and measure what is the live load that is being exerted on that building. Okay. And I do it for 100 days. I find that on 95 of these days, the value of load was greater than this was lesser than this particular value. Only on 5 days, the value was greater than this value. So I would design my slab or my system for this value of that load.
You mean for the greater load that you
Sorry,
experience on the 5 days?
sorry.
You mean the greater load? Am I audible?
Yeah, you're audible. Please go on.
So you design the slab for the amount of load experienced on the 5 days when it was greater.
No, we will design it for the value above which only the load was greater for 5 days. Do you understand?
And
So
the
the
opposite happens in strength.
Exactly. The opposite happens in strength. So we take a value which is lower bound. So we take a value below which only 5 blocks are failing. And we take a value of load uh, in which only 5 of these days the load was exceeded. So we are overestimating. We are overestimating the amount of load, and we are underestimating the strength. It has
so
this strength. It can take this amount. The maximum strength that this can take is this. But what we are doing is let us consider the lower bound strength and let us consider the upper bound load. And let us make sure that the lower bound strength, which is this value, is greater than equal to the upper bound load.
so it shouldn't be that even the last five that fail,
Yeah.
they should sustain more load than the 5% load that cause that we designed for.
Sorry.
So what I mean is, even the last five that fail, the last five units that fail, should be able to take much more load than the than what we designed for, than the five higher bound load that we designed for.
In that case, there is zero possibility of failure. The case that you're talking about is the upper graph that you see.
Yeah, yeah.
Okay.
So
In
this is
that
what we
case,
are
there is
aiming for, right?
uh, no. In that case, there is zero possibility of failure. What that will do is it will make the structure uneconomical. Okay, so we kind of try to design it in such a way that it is safe and it is serviceable. So this, when the graph that you see on the lower portion suggests that there is only a slight possibility of failure of the structure. Okay,
Okay, yeah.
and when is that possibility? That is when on one of the 100 days wherein the loading is more than characteristic load, on the slab which is designed from the concrete, which has the strength of the five blocks that we say that are failing below a certain value. So we are targeting for that possibility of failure. So the question that you asked, for that the probability of failure is zero, but that is going to lead to an uneconomical structure. For an economical structure, we are going to see that the possibility of failure of the structure is only 5%.
So in
Um,
the lower graph,
Sorry.
go ahead.
Yeah, yeah.
Yeah, so in the lower graph, where the graphs are meeting, the
Yeah.
1 point, so there the capacity is equal to demand, right?
Yes.
Okay. And so the shaded part, the failure part, is
Yes.
where the is where the demand gets more than the capacity.
Yes.
So why can't we have a structure which so now like in the upper graphs it's like it shows that the capacity is much more than the demand, right? Like the safety
Yes.
margin is a lot. So can't the
Yes.
safety margin be reduced but even even while keeping it safe? Like what's the point of having a 5% failure option?
The point is that uh, see, even 5% chance of failure is a very low chance. You see, historically, almost all the buildings that we have built have lasted their design life. Okay, so none of the buildings have failed because we had this very conservative because we were having a very high chance of failure. So it has been with the theory of probability, it has been found that okay, it is safe to have a certain possibility of failure of the structure, and okay, 5% is a good number. If you are aiming for 100% possibility of safety, or if you are aiming for a 0% probability of failure, you're going to need much more thicker columns. You're going to need much more deeper slabs, deeper beams, and the structure is going to be heavier and uneconomical. Okay, so what we are trying to do is we are trying to achieve economy by setting a certain standard for how safe the structure should be. Okay,
Yeah, so this 5% is like how is it decided that it'll be
it is
5% failure or 95% it won't?
it is based on the theory of probability. Okay, a lot of data from different structures over different with different loading conditions and so on, and then there's this theory of probability that has been worked on in this data, and then we got this number. Okay, let's say that the structure, let's say that there's only 95%, there's only 5% chance that the load will exceed it, or there's only 5% chance that that we will have a strength of the material less than this value. Okay, so this is based on the theory of probability.
Hello.
Yeah.
So here, when capacity is equal to demand, the structure
Yeah.
should still sustain, no? So like when the demand is more than capacity, that is when it should fail, right?
Yes.
But
And
here, when it is equal, still, why is it a failure?
Um, so the five blocks that would fail will
yeah,
only fail if there is a spike. There's a 5% spike in the load. right? That's what we're aiming for.
Okay, to answer her question first, okay, this is a point when demand is equal to capacity. That's a limit state, okay? A state of impending failure, okay? If we take one step ahead, the structure is going to fail, and that is what this graph uh, conceptually shows. If your load is slightly greater than this, we could say that the structure has failed. Okay, it does not fail per se when it is equal to when capacity is equal to demand. When capacity is equal to demand, that is the limit state. That's it. You cannot load it anymore. If you load it, it has failed per se. It's not that it's immediately going to collapse, but for our design or for theoretically, the structure has failed.
Okay,
Did I
understood.
did I
Yeah,
answer your question?
yeah.
Any more questions? Okay, moving on. So what I've done now is I have put all these points in only one graph, okay, or in only one stress strain curve, and let us try to understand various points on this graph, okay. So green is what is the yield strength. Everybody understands? Green is a yield strength. We have seen in the last lecture that yield strength is kind of the maximum stress that we are targeting. We cannot load the material more than this value of strength. So this is the ultimate capacity. Okay, and say uh, pink is the stress that develops under normal loading. When there is, say, taking the example of college building, when we have say a normal weekday, classes on all floors and so on. So this is the value of stress which develops at what is called as working load. Okay, which develops at what is called as working load. So what we do is we underestimate the strength by dividing it by a factor. This factor is called as partial safety factor for material. What we did is we are underestimating the strength and we bump up this load by multiplying it by what is called as partial safety factor for loads. Okay, so we underestimate the strength, we overestimate the demand, and the difference between these two is what is the safety margin. Okay, so the green that you see here is the ultimate capacity. What I did is if from the test I find that the ultimate capacity is 100, what I did is I divided it by a factor to account for all the uncertainties in the material. Okay, like manufacturing tolerances, imperfections, possible deviation of material strength from assumed value, and so on. I considered all these factors and divided the ultimate capacity by a factor which is called as gamma m, or the partial safety factor. So now I'm targeting the blue dot here. I'm not targeting the green dot anymore. I'm targeting the blue dot because there are certain uncertainties. Okay. Now, this pink dot is the stress under working loads. But this is this is under normal conditions. What might happen is tomorrow you might just have a fest, or tomorrow you might just have an exhibition, and you will have a lot of people. So there's uncertainty, right? So there is a possible deviation. There's a deviation of loads from specified values. Say today it's a college. Tomorrow it might be used as another building that would have higher loads. Okay, to take care of all these uncertainty in loads, what I did is I multiplied by a factor which is called as partial safety factor for loads. So now instead of this, my loads are this, and the difference between the blue dot and orange dot is the safety margin. Is the safety margin. So to put it in an algorithm, the strength should always be greater than load effects, or the capacity should always be greater than demand. For that, okay, before that, so when we divide the ultimate capacity by the safety factor, we get what is called as the design capacity or the design resistance. And when we multiply the working load by the safety factor, we get what is called as a design load. Or this is the load for which you have to design, and this is the strength that you're going to use for design. So the strength should always be greater than load effects, or the design strength should always be greater than design load effects. For that, what you do is you should always underestimate strength, or you should have the lower bound strength, and you should always overestimate loads, or you should always consider upper bound loads. Meaning that, how do you underestimate? You underestimate it by dividing by a factor, and you overestimate the loads by multiplying by a factor. Both these factors are greater than 1, by the way. So we underestimate the strength and we overestimate the loads. So characteristic load, multiply it by a partial safety factor, you'll get a design load. Okay. Characteristic strength, divide it by a partial safety factor, you will get design strength. And this design strength, or this green block, should always have a higher value than the red block. Do you understand?
Yeah, but wouldn't this give you an uneconomical?
This is, see, all this is to make sure that the structure is economical and safe at the same time. Okay, just imagine the World Trade Center could have been designed for resisting blast load. But what would happen? The structure would get highly uneconomical if you design for that. Now, what is the possibility of uh, occurrence of that particular event? And that possibility fell under 5%. Okay, this is just a loose example. Don't. This has nothing to do with the theory that we are dealing with now. But what I'm trying to say is, if uh, the entire point of doing is to make sure that the structure is safe and economical, and this is the theory behind it. You make sure that the structure sustains not only normal loads but also unprecedented or higher loads. Okay, to account for
Okay.
that, we multiply by a factors of safety, so that we have higher loads or we have upper bound loads, and you divide by a partial safety factor. You divide the strength by a partial safety factor, so you get a lower value of strength. Okay, underestimate strength, overestimate loads. Understand? Is it too heavy to understand?
No, 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 got it, got it.
What about others? Okay, anybody who has not understood anything about this? Do we have someone? Don't worry, I would not ask a name. I would just explain it again. So,
Uh,
yeah.
I just had a doubt. So, like, you design for the 5% of the load that exceeds the limit, and the
Okay.
95% of the strength that is below
Okay,
the
okay,
limit.
okay, okay, okay. So let us differentiate between that 595 and let us differentiate between partial safety factor. Okay. So that 5%, 95% is only to define this now, this green dot and this uh, pink dot. Okay. So this 595% concept is limited to characteristic load and characteristic strength. That's it. Okay. So we have moved to a new topic here, wherein now we are trying to understand as to how can we multiply or divide it by partial safety factors so that the structure is safe. So if I have a certain value of characteristic load, which is the ultimate capacity, this is already the 95% thing. This is already done. Okay, the green line already corresponds to characteristic strength. The pink line already corresponds to characteristic load. Further, what we are doing is we are dividing the characteristic load by a safety factor. We are multiplying the characteristic load by a safety factor. And this is that safety margin. Okay. So this characteristic load, which is this pink line that you see here, this characteristic load multiplied by safety factor, get a design load. The characteristic strength, which is this green line here, divided by gamma m, and get what is called as a design strength.
Understood. Yeah.
Okay. Any more questions? See, please don't shy away if you have a question, because nobody is going to ask you this in the exam per se, but you will at least understand what are we doing when we look at various formulae. Why is it that I multiply by a safety factor here? Why is it that I divide by a safety factor here? And why is it that I'm targeting at least this particular value of load? So it is just a basis. Nobody is going to ask you to define or ask you to define what is a limit state method, or what is the explain the design philosophy of limit state method. This is just for your understanding, and this same philosophy will be used in the design of concrete structures. Okay, so please don't shy away from asking any questions. Okay, how much percent of this have you loosely understood? Say 50%, 60%, 80%, 20%. Anybody?
Yeah. Interestingly, I understood the second part, like the dividing and multiplying by the safety factor, but the first part, I kind of
Perhaps
still
more
understand
work is
complete.
required on the first part.
Yeah,
Okay, what's your name?
Ishan.
Ishan. Okay. Uh, okay. So what is important to us is the second part. Okay.
Okay.
Sayukta, do you want to say something?
So maybe I myself will go back and
Yeah. So please just go through this once, and if a majority of you are not understanding this, we'll look at it again. Not a problem. Okay. So now let us look at what these safety factors are. Okay. Now these are partial safety factor for material, meaning we are going to divide our strength by these numbers. Okay, we are going to divide our strength by the numbers that you see on the right. So again, the numbers are different for different types of failure. Say the failure which is governed by yielding has a partial safety factor of 1.1. The failure which is governed by buckling has a partial safety factor of 1.1. The failure which is governed by ultimate stress has a partial safety factor of 1.25. Okay. The reason why we have different numbers, see, my uh, the objective here is not to remember these numbers. The objective is to understand what these numbers mean or what these numbers signify. Okay. So we have a higher, so the failures which are gradual, like yielding is a gradual failure. You saw that flat portion in the graph. So we have a certain safety of margin there inherently. When the failure is gradual, you have a lower safety factor. When the failure is sudden or when the failure is brittle, you have a higher safety factor. You have a higher safety factor. So it depends on what is the type of failure. If it's a yielding failure, a buckling failure, there is a lower safety factor. If it's ultimate stress, there is a higher safety factor. Now let us look at partial safety factor for loads. Okay. So the partial safety factor for dead load is 1.5, meaning that if the dead load of your slab is say 4 kilonewton per meter square, you multiply it by 1.5, which gives you 6, and then you design it for a load of 6 kilonewton per meter square. Do you understand? The partial safety factor for live load is 1.5 when you have a, a combination, or what is called as a load combination, or when multiple loads are acting together. say you have dead load plus live load plus wind or earthquake load, you have a partial safety factor for 1.2 for each of these. That is, you will design it for 1.2 times dead load plus 1.2 times live load plus 1.2 times earthquake load. Okay? Can someone just imagine an answer? Why is it that we have, when it is dead live, we have 1.5. When it is dead live earthquake, the 1.5 is reduced to 1.2. Can someone answer this question?
Because the probability is very less.
Exactly. Because the possibility of having a party on the day of an earthquake in a building that has a heavy dead load is very less. The possibility of all the severe loads acting at one point of time is very less. And therefore, this signifies the probability 1.5. It's highly probable that it would have a higher dead load, but higher dead load, higher live load, earthquake at the same time is has a lesser possibility, and therefore we move it down from 1.5 to 1.2. Okay, when it is only dead plus wind or dead plus earthquake, it is 1.5, and for all limit states of serviceability, it is 1. Can someone answer this question? Why is it that for limit states of strength, we have factors greater than 1, but for limit states of serviceability, we consider the actual load? Or why is it that we use a factor of 1 for limit states of serviceability? Can someone answer this question? Okay, sometimes I just feel that this system or this kind of setting that we have is just like, have you seen Dora the Explorer? So Dora just asks a question, waits for some time, and then answers the question. So, uh, let, so let us just try. So let us just try
Ironically,
to.
that's the exact same thing that we use to compare the system.
Yeah. So it's. See, the class in normally. Okay, I'm not like patting my own back here or something, but normally the classes are much more interactive and they are much more fun. But there are two things here. One is that there is no way for me to understand that you understand, and second, we are on record. Okay, so I have now this the kind of we have to limit the content of this, which is only uh, concerned with the subject. We cannot wander here and there, and then maybe come back. It's all on record, so I have to be a little careful when I say things. So it's much more fun. I mean, you will realize it if we happen to get a chance to start an actual class. This is much more easier to explain when I'm in front of you. Um, I can draw things on board, do examples. It's very easy to understand. So this particular setting, it's a little difficult. I understand, but it really helps when you talk. Yeah, it helps. So anybody which has an answer, oh, why is the limit state of serviceability has a factor of 1 against all the limit states of strength that have a factor of greater than 1? So the reason is that we want actual deflections. We want uh, we want the actual set of vibrations. So we want the actual. We are not interested in the deflection at an ultimate state, because at an ultimate state, the structure is failing. When a structure is failing, we're not interested in, okay, how much is the slab deflecting. It's failing. So deflection is not a concern then. Deflection is a concern when the building is still in use. So we want to consider deflections at actual loading. Okay. In an event of failure, we're not going to worry of how much is the deflection. All we're going to worry about is uh, making sure that the building is not used anymore. So deflection or serviceability is something that we look at actual working condition, and therefore we use a factor of 1. Okay. So with this, we have covered the basics of design. I know this is a little heavy, and this is very new for you, but we'll get a hang of it as we solve problems, as we look at these factors every now and then. Okay, gamma m, gamma l. We look at these factors in almost all these equations that we're going to use. So we'll get familiar with this over time. But what I really suggest is, when the class is over, during this week, go through this presentation, try to understand what each of these slides mean. And if you have any questions, we can always discuss in the next lecture, but please go through this presentation. Okay? So, any questions? Yeah?
Can you go to the
Could you
last slide?
explain?
Just a moment. The last slide, this one, right?
Yeah. Yes.
Okay. Okay.
So now we are here we are considering the safety factors in very kind of specific conditions, like only for when there is dead load and the live load, and when it is differently loaded in different conditions. So then,
Yes.
while designing, we should have some one final value, right? For which we design. So how do we arrive at that?
Yes, that's a good question. Just let me get to a particular table in IS 800. I hope you remember what is IS 800. Anyway, it is a code that we're going to use. So this this particular table gives various load combinations. Okay, we design a structure for various possibilities of load combinations. The first and the easiest possibility is dead load plus live load. Okay, there is no other load on normal days. It's only dead load and live load. For that, we say our first design combination is, okay, let me do it this way. So our first design combination is, oh, so our first design combination is, say, 1.5 dead load plus 1.5 live load. This will give you a certain value, say x. Our second design combination is, say, 1.2 times of dead plus 1.5, sorry, 1.2 times of live plus, say, 1.2 times of earthquake. This will give you a certain value of load. Okay. Let us look at our third combination. Say 1.5 dead plus 1.5 earthquake. This will give you Z. What you do is you take the maximum of X, Y, and Z, and then you design the structure for this maximum value. Did I answer your question?
Yes.
In now we have a very limited combinations in small buildings. Okay, but in case of very tall buildings, there is something else that we have, which is called as the wind load. So what we do is we replace this earthquake with wind. And even though the code has a limited number of combinations, but for a majority of tall buildings, we do what is called as wind tunnel testing. Heard of this term before?
Yes.
In wind tunnel testing, there is this model of the structure that is prepared, and then wind is applied from various directions. And then it gives a number of combinations. So it gives, say, more or less 24 combinations of wind only. Okay. So when we combine, so let me just, so you say wind in X direction, or wind at 0 degrees. Then we have, say, wind at 90 degrees, wind at 35 degrees, and so on. So for a particular structure, we consider wind in all directions, and then we select the combination that gives the maximum load. So just to put it loosely, the average number of combinations, or uh, the number of combinations that we develop using this is about 72. So you input all these load combinations, and then you select the combination that gives the maximum value of load.
So out of these 72, it's the maximum one, or is it like an average of these 72?
Maximum one.
Okay.
Okay, maximum one, not the average. Because the structure has to sustain the maximum load, not the average load. Okay. Okay, this 72 is just a number for your understanding. Okay, this is not the absolute number. It is not that you have only 72 combinations. It varies. It varies structure to structure, and it varies what is the type of wind tunnel testing that you've done. It varies. But the number that I loosely remember is having 72 combinations. In some cases, you might have more than 100 combinations, 150 combinations. It all depends on what are the different cases that you're considering. That's it. But the point being that we want to consider the highest load that is going to act on that structure. Okay. Someone else had a question.
Yeah, I wanted to just ask about this one, like limit states of serviceability. Why is it one? I didn't understand that. Like, why is
Okay.
it?
Okay. So you are concerned about your comfort during the working condition of the structure, right? Okay, this is a very loose way of putting it. Okay, this is just ghar ghar ki kahani understanding. Okay, this is not what it means. I'm just trying to put it in very loose terms. So you will care about your comfort under normal conditions. You will not care about your comfort when an earthquake occurs. Okay, serviceability is a measure of how comfortable you are in using the structure. So we want to uh, measure serviceability at working loads. What happens in case of ultimate loads? Okay, these are ultimate loads. What happens in case of ultimate loads is the structure is on the verge of failure. So when the structure is on the verge of collapsing, you're not going to care about your comfort. You're not going to care about, okay, how comfortable I'm this with this slab deflecting so much. You're not going to do that. You are going to care about your comfort only under normal conditions of the structure, not when it is about to collapse. So that is why we take care of the serviceability, we care of deflection, we take care of vibrations, fire, and so on under normal conditions. Okay, so the structure should be serviceable at normal loads, and it should be safe at ultimate loads.
Okay, so in like fire and all comes under serviceability then, like.
Fire safety comes under serviceability. Yes. This
Okay, so when the
the
damage is not done to the whole building and it's at a.
yes. So there are. I've told you this before. There are various fire ratings. There is a 2-hour fire rating, 4-hour fire rating, and the structure is fireproofed accordingly. Okay. So this 4 hours or 2 hours is basically a period during which all the important people, or no, all the people and all the important stuff could go out. So it is a serviceability condition. Okay, fireproofing is also comes under serviceability.
Okay, got it.
Also in the fourth point, why is there so much variation from zero point 0.9 to 1.5? Dead
Okay,
load plus wind earthquake.
okay, that's a good question. Uh, I deliberately did not explain it because I did not want to increase confusion. But let's look at it. Okay, so we have two possibilities. One is 1.5 dead plus 1.5 earthquake. Okay, another one is 0.9 dead plus 1.5 earthquake. You can see this combination, where it is here, 0.9 dead plus 1.5 earthquake. So this is that combination. Okay. Now, there are two different situations for which we consider these combinations. Now, we consider this for the normal strength design. For the normal strength design. Pardon my handwriting. Pardon my digital handwriting. So, this is what we consider when we have to uh, when we have to test the structure under against overturning. Okay, if this is the structure, it is subjected to some lateral loads. It is naturally going to have a tendency to overturn. Okay, what is stopping it from overturning? It is its own weight. It is its own weight. So, when we are testing overturning or when we are uh, analyzing the safety of the structure against overturning, we do not want to overestimate the dead load. Did you understand what I said until here? When we are analyzing overturning, in which dead load is our friend, okay,
Yeah,
we do not
somewhat.
want to overestimate dead load. Okay, so what we do is we underestimate dead load when we are considering it for overturning. See, we always underestimate our strength and overestimate the load. Here, dead load is what helps us. Whatever helps us, we underestimate that. Whatever works against us, for example, the loads, we overestimate that. This is when dead load works against us, and therefore we have to overestimate this, we have to overestimate this. This is when dead load works for us. We underestimate the dead load, we overestimate the earthquake load.
But why does the dead load help us?
The dead load help us is because it is because of the dead load that the building is not overturning. Simple.
Okay, yeah, got
You
it.
just
Yeah,
take a bottle full of water and you try to apply a lateral load. Why is it not overturning? It is because of the self weight of the bottle.
yeah.
The moment you don't want to overestimate the self weight, okay, because that is helping us make sure that the structure does not overturn. Do you understand the point? Whatever
Yeah,
helps
yeah,
us, we underestimate it, and whatever works against you, we overestimate it. Could I answer your question?
Yes,
yeah,
yes,
got it.
got
Yeah.
Okay. Any more? That was a good question, by the way. Who asked it?
the Ishan.
Ishan. Okay. So we have Ishant and Nishanti, right? Nishanti is a different. Okay.
Yeah, I'm here.
Okay. Okay. So any more questions? So I understand that we are going dead slow right now. We have already completed 3 lectures of 150 minutes, and we should have completed at least one design topic. But this is just the start. We'll pick up as we move on, and as we kind of set a chemistry that I understand what you understand, and perhaps I could put it in a better way that you understand. So we're taking it a little slow right now, but as we move on, we'll have to pick up speed because we have limited time this semester. Anyways, I was planning to finish one more topic, which was tension members. Unfortunately, we don't have any further time because we also have a quiz. So should we do it now, or do you want a 5 minutes break and then do a quiz?
A break.
A break of 5 minutes?
Yeah.
Okay. So we'll start the quiz at 10:20 and we'll finish at 10:30. 11:35. Oh, sorry, 11:20, and we'll finish at 11:35. Okay?
Yeah.
Yeah, take a 5 minutes break. Uh, in that period, if anyone wants to discuss something, has questions about what we have learned or about anything else that you're working on, uh, you're welcome to ask.
Bhargav, I have a question.
Yeah, what's your name?
Devishi.
David.
So,
Okay.
yeah, it's from uh, when we were discussing limit states of strength.
Yes.
So, is limit states of strength like the maximum stress point for structural material? Like
You could.
when we were doing last class the graph for the stress strain curve,
Yeah.
there was a point in the graph where the stress was maximum, right, for the 100 strain or something.
Here, this point.
Yeah, the the high point, is that
Yes.
like the limit states of strength for a building?
Mm, So let us talk about this graph first. We do not target this stress. We limit ourselves to this stress. Okay, because this is the point until which the structure is not undergoing any plastic deformation. Okay, when we unload the structure, it will get back to its original position. So the maximum value of stress that we are targeting is this green value. Okay, we don't want to go until this value, right? Because if we kind of go until this value, it would have undergone a lot of deflection, and then it might not be practically possible to use that structure.
Okay, so the high value is like the extreme conditions which won't happen probably.
Uh, okay, let me answer your question. So we are for this uh, referring to this graph, we are always targeting the yield stress. Okay, now a limit state is is a value or is a combination of loads or is a state wherein either we have a material failure, which may be because of we have reached this green point, or it may be because of member failure. Okay, it might happen that the column has buckled. So in buckling, the material is okay, but the member has failed. So it does not necessarily mean that the material has failed. What it means is either the material has failed, or a member has failed, or the structure itself has failed, say by overturn. So there are different modes of failure. It might be the material failure, member failure, or a system failure. So in limit state, any one of these might have been reached. Did I answer your question?
Yeah, so the highest point of stress in this curve, in this graph, is the extreme. Would that be the extreme conditions of loading?
When you say highest, do you mean this point here?
Yeah, yeah.
Okay, again, we are not targeting this. Even for an extreme loading, we are not targeting this value. What we are targeting is this green value. When the stress reaches the green value, there itself we are saying that it has failed.
Okay.
Meaning that when in one of the limit states, it might happen that the stress has reached the green value. There itself we say, okay, failed.
understood. Understood.
Okay. Any more questions? Are all of you back? Can we start the quiz?
Yes, we can.
Anybody who needs more time? Okay, I take it as a no. Okay, Madhura, I just read your message. You couldn't have 10 minutes, but you 5 minutes. You have to finish by 11:30. Anyways, should we start? Everybody on board?
Yes.
Okay.
Yeah.
Great. You know the drill, okay? You can use whatever resources you want, okay? So just submit it on time. That's the most important. There you go. And for the roll numbers, you already know what to do. Those of you who do not have a roll number, just follow same what you did last time. Put it 0000. Put your name and leave a note. I've tried to keep this quiz relatively simpler than the last one. Okay, do you guys need more time?
Yeah, just a
Yes.
minute.
Yeah, could we get like
5 minutes.
40 time till 40?
Yeah.
Until 40, I'll let you know. So, okay. start submitting. But close it at 38. Okay, I'm at 50. Please submit right away. I'm gonna close it at 39. Please submit right away.
Bhargav, you're not audible.
Hello.
Yeah, you're audible.
Yeah, so please submit right away. I'm closing it. The last 15 seconds. 10. 5. Okay. So the graph looks much better now.